Namaste, this is H.C. Verma from IIT Kanpur, and I am here to deliver this special lecture on experiments, short experiments, simple experiments in mechanics, which can be related to some of the laws, some of the equations that you study in the course. Physics, as you know, is omnipresent, and whatever is there around us, all these classical mechanics, electricity, optics, those rules are in front of our eyes. So it's a very good opportunity to learn the physics laws and equations and everything through these small events which are taking place around, and manipulate them little bit to tune it for our own syllabus, understanding the laws, the topics, the subjects that we study, and then enjoy all these equations together with the natural events. So most of the experiments that I will be showing today will be such that you can also design them in your own house and you can perform that. We have done it ourselves, most of them, and you can enjoy and you can come out with even newer experiments. So I will be taking some 3-4 topics. One is friction, another is non-inertial frames and pseudo forces. Then we will talk of rotations and possibly little bit of resonance in forced oscillations. So let me start with a common experiment which is there in textbooks, which is there in literature for long time, maybe 5, 6, 7 decades, and that is known as card coin experiment. And by the name, maybe you may be knowing with what experiment I am talking of. You take a glass, you take a card, you put a coin, you flick the card, and the coin falls in the glass tumbler, and that is popularly known as a demonstration of inertia of rest. So I will start with that, but the discussions will be somewhat different from the traditional ones. So let's start. So here is a glass tumbler, and this important item of my experiment can be found anywhere in your house or in tea shops or lassi shops. Then I have cards, several cards. I have a card of longer size, smaller size, still smaller size. We have several cards, so that is another part. And the third part is this coin. This is a coin here. So the experiment consists of putting a card here on this tumbler. So I am putting this card on the tumbler, and then this coin goes here on this card, nearly at the center, above the center of this glass tumbler. Now the prescription is you flick the card and then the coin should go into the tumbler. So let's see what happens. Oh, it did not go into the tumbler is still empty, and the coin is here outside. Okay, so let me do it again. Same card and the same coin, and let me do it again. This time it goes in the tumbler. Okay. So let us take a longer card, this card. Let us take this longer card, put this coin here, and then flick. It goes outside. Let's repeat. Goes inside. So what do you see? The coin sometimes goes into the tumbler, sometimes it doesn't go into the tumbler. The popular explanation is that when the card is flicked, the card moves ahead, but the coin, because of its inertia, remains at its own position. And if that happens, when the card slips out, then the coin should go into the tumbler. Since in our experiment sometimes it goes into the tumbler, sometimes it doesn't go into the tumbler, so something else is involved into it, and let us see what that something is. And you must have guessed that something is friction. It is friction between this card and the coin. When this card goes out like this, it slips, the coin slips on the card. When I flick this card, what happens? The card moves in the forward direction. And then there would be a slipping of the coin on this card. And once there is a slipping, there will be friction in the forward direction. Friction on the coin will be in the forward direction because it is slipping on the card in the backward direction. And that friction which is on forward direction will take this coin in the forward direction, and therefore it must move in the forward direction. So what happens? If this movement is large enough, the displacement of the coin is large enough, more than the radius of this tumbler, it falls outside. And if this movement is less, then it goes into the tumbler. But in all cases, there will be a friction on the coin and on the card also, and that friction will take the coin forward. That displacement may be small, may be large, but it is always there. You can make an estimate, you can write your equations and find conditions, in what condition this will go into the tumbler and in what conditions it will go outside the tumbler. So you must have done this in the main course on mechanics, that Newton's laws of motion, first law and second law, they are valid. You can apply it in that particular form only in inertial frames of references. If you have non-inertial frames, you have to use some pseudo forces if you still want to apply F equal to ma. So if the frame is moving in a straight line, accelerated frame is moving in a straight line, so the acceleration is linear, no rotation of frame is involved, then the pseudo force is very simple. That pseudo force is just minus m times a naught, where m is mass of the object under study and a naught is the acceleration of the frame. It is some kind of an artificial construction. You are taking mass of something else and acceleration of something else and then multiplying and putting a minus sign. But in any case, if you want to use non-inertial frame and use Newton's law, you have to bring some artificial things. So that is why this. So this force, if you include together with the real forces, you can still analyze the things. So let us do an experiment on this. So here is a plastic box, and in this box what I have put is some kind of these pulses. Sometimes it becomes a rare commodity, and this is all spread on the base, and I close the lid. This slab is our inertial frame and it is stationary. There is a resultant force on every particle is 0. Everything is at rest. Now let us talk of this box frame, and I will give an acceleration to the box in the direction which is left with respect to myself. So I will be accelerating it on this line, and you see what happens to these pulse particles. So these are our object. So we will be looking at the motion of these pulse particles with respect to this frame, box frame. So I am going to give the acceleration, and you watch carefully and see what kind of motion takes place with respect to this box. Okay. So once again, this is at rest and it is almost uniformly spread on the base, and then see if they are moving towards left or they are moving towards right, what kind of motion is this. So what did you observe? To begin with, you found that these pulses are getting accumulated on this side. So they had an acceleration with respect to frame in this side, and that is understandable from our equations. Since the acceleration is in this direction, left with respect to me, the pseudo force minus m into a naught is opposite, in opposite direction, that is towards right with respect to me, and hence because of that pseudo force these particles were accelerated towards right and things got accumulated. But then you also found that finally the things were accumulated on the opposite side. If you have not seen that, see it again. See, finally what is happening? More of the particles are accumulated on this side. So in that second half, the pseudo force is towards left as seen by me, so in this direction. And that is definitely it should be like that, because if I have accelerated, I have given it a velocity, but then I have also stopped it in the second half. So if I am stopping it, it's a kind of deceleration, and the acceleration is opposite to the direction of velocity. The pseudo force is towards left as seen by me. So the same story, but this time in a different packaging. So I have a bottle or a vessel, and in this vessel I have water, and in the water a ball is hanging. This ball is hanging and the thread is fixed to the lid. So this is how it is at rest now. The net force is 0. Again this box will be our frame, which at this moment is inertial frame. It is fixed in the lab, which we take as inertial, and since it is at rest, the resultant force is 0 and all those things. Now I will accelerate this box again towards left as seen by me, and you see what happens to the ball. The first go, look at the first go, in which direction did the ball deflect? Once again, let it stop. Okay, now the oscillation amplitudes are quite small. So the first throw, look at the direction of the first throw. I am taking it towards my left. It first goes and hits this wall. Okay, so since I am accelerating it towards left, the pseudo force is towards right, and that deflects this ball towards right and goes and hits this side. Of course, later it makes oscillations and all those things happen. So once again, last time. Okay, it goes and it hits here. All right, now a second version of this experiment. Again I have a vessel, again I have water, again I have a ball, yellow ball, but this time this yellow ball is not hanging from the lid. This yellow ball is attached to a thread, and that thread is fixed at the bottom of this box. This yellow ball is a tennis ball, and it's lighter than water, so it floats in water. And since we have fixed that thread at the bottom, it is just staying at the middle. So you can also see the thread, I believe, below this yellow ball. You can see the thread which is going at the bottom. So once again the frame will be accelerated towards left, and you see the direction of the first throw of this yellow tennis ball. in which direction does it move? Could you observe the first throw? In which direction did this ball move? Did it move towards left or it moved towards right? Acceleration is towards the left. Initial acceleration at least is towards left. Okay. So it is going towards left. It is going in the direction of the left, whereas the pseudo force should have been towards right, opposite to the acceleration. So what is happening here? What is happening here is, together with the pseudo force, you have real force also. When you accelerate this vessel, the pressure of this water is no more same on the left and the right. When it is at rest, it is the pressure at any horizontal level, all points in any horizontal plane, the pressure is same. So this side pressure is same. Up and down the pressure is different, but if you go this side, the pressure is same. But once it moves, on water also you have pseudo forces, and those pseudo forces try to push the water in the opposite direction, and hence the pressure on this side increases, pressure on this side decreases, and you have a real force. Because of this pressure difference, you have a real force, and that real force dominates over the pseudo force. The force due to pressure difference is more in this case as compared to that pseudo force, and hence if you write F equal to ma, including the pseudo forces, including the real forces, the total net resultant force, including everything, you do have a final resultant towards this left direction, and that is how it moves in the left direction. Okay, so next experiment on this non-inertial frames, linearly accelerated. Here I have a plastic box, and on the lid I have fixed a small black ring magnet here. This is fixed to the lid using this double sticky tape. And then in the box itself I have put one more similar black ring magnet, and if I close it here, these two magnets, one magnet here and one magnet here, they are in attractive mode. The facing poles have different polarity, and therefore they are attracting each other. But these are weak magnets, and at this distance the force of attraction is very small, and therefore weight of this ring is quite high as compared to that small force of attraction, and hence it is staying here. The box frame now is inertial frame. So you can use all your Newton's laws. There is a normal reaction force from this bottom, then there is weight, then there is small feeble attraction from the upper magnet, and the total is 0, and hence this magnet remains at rest with respect to this box frame. What I will do, I will just drop it from here. I will just drop it from here. The box will go down, and since the magnetic force is quite weak, almost it will go with the acceleration due to gravity small g. So this box will become a non-inertial frame, an accelerated frame, and the acceleration will be almost g downward, and in that falling box frame, that accelerated frame, you see what happens to this lower ring magnets. So now I am going to drop it and try to see that lower magnet, how it goes in the box. Possibly you won't be able to see that, but there's something else from which you can work out what is happening to this lower ring magnet. So I'm dropping it. So where is that magnet? Where is that ring magnet? Where is this ring magnet? It is not here. So it has gone up and has got stuck at the lid. Now you have two of them. You started with one of them on the lid, but now you have two of them. So it goes and sticks here, and when it goes and sticks, it makes a sound. Okay, when it goes and sticks, it makes a sound. So I'll repeat this experiment, and you follow the sound, because that sound tells when it goes and hits up. So I'm doing it again, and you follow the sound. Okay, you must have heard that sound as soon as I drop it. Immediately after that, in a very short time, you hear the tick. So in the box frame, this lower magnet has gone up and gets stuck to this upper magnet. So if I analyze from the box frame, what I will say is, since the box is going with an acceleration g downward, there is a pseudo force on this lower ring magnet upward. And how much is that? That is on the board. Minus mass times acceleration of the frame. So mass of this ring magnet and acceleration of this box. So what is happening? M, and what is the acceleration of the box? Almost g, so mg. In which direction? Upward direction. So the real force mg, that is the weight which is downward, gets exactly cancelled by, exactly means assuming that it box is going with acceleration g. So it gets cancelled by this pseudo force. So weight and the pseudo force, that sum is 0. So let me make it on the board. So I am talking of this magnet. This is my object. Its mass is a small m. So the pseudo force is minus mass of the object and times acceleration of the frame. So this acceleration of the frame is g and mass of the object is m. So this is it. But then you have a real force, weight, which is, so this is minus mg and this is plus mg. So this is plus mg. So that means you have mg force which is upward, and here mg force which is downward. And then you have this magnetic force, very small feeble magnetic force, force of attraction. And this is in upward direction. So I am talking of this ring magnet. That upper magnet which is sitting here on the lid is attracting it up. So that small force is this magnetic force. Weight is there, and then the pseudo force is there. There is a normal force here also, but that anyway goes to 0 once the motion starts. So these two cancel, and this is the only force remaining. So that is equal to mass times acceleration. Acceleration of this ring magnet with respect to this box, that is the acceleration which is coming here, and that is in upward direction because the net force is in upward direction. So it goes up and it goes and hits this magnet. So that is how this phenomena is sometimes called weightlessness, because the weight gets cancelled by the pseudo force. So if you are in a freely falling frame, freely falling box, you forget to apply pseudo forces and you also forget to apply the weight, and still your Newton's laws will be okay and you will feel as if there is no weight. So this phenomena is sometimes called weightlessness. Okay. So another kind of non-inertial frame you must have studied is rotating frame of reference. If you have your XYZ axis such that in the lap frame these axes themselves are rotating with some angular velocity omega, and in that frame if you are doing the analysis you have to apply certain pseudo forces. One of them is called centrifugal force, and the expression for that you must have done that. Centrifugal force you write it as m omega square times r. And what are these quantities? Suppose this is the axis of rotation and the frame whatever frame. You can have a disk. Suppose you have a disk and the disk has x-axis marked on it, y-axis marked on it, z-axis marked on it, and about z-axis it is rotating with some angular velocity omega. So omega is the angular velocity of the frame, rotating frame, and this r is the distance of the object from the axis of rotation, and this m is of course mass of the object. And what is the direction? The direction of this force is outward, away from the axis. So this is a pseudo force. So here I have a disk, and this disk can rotate, right? This disk can rotate. So this disk will be our rotating frame of reference. We can mark x-axis, y-axis on this. We can say that, okay, this is our let us say x-axis, this is let us say y-axis. You can mark it like that, so that when the disk rotates, this x-axis also rotates, y-axis also rotates in the frame, and here is the axis of rotation. That z-axis is the axis of rotation. So in this rotating frame, what we want to analyze? So I have a tube here, a long glass tube. I have this long glass tube which is of course closed here, and here we have closed it with a cork. In this I have water, and in the water you can see there are certain red colored particles, these ones here. Here you can see some red ones here, here there is a red one. So there are red color things which are at the bottom of this tube, right? They are here. And then you can see some white, these white parts, white particles, and these are the one yellow here. So these are foam particles, foam pieces, and these foam pieces are floating on the water. So they are at the top, on the near this surface, and these stone particles, the red ones are stone particles which are at the bottom, and they are distributed everywhere in this tube. You can see a particle here, a particle here, particle here, everywhere it is distributed along the length. Now I will rotate it, and you see what happens to the foam particles and what happens to the stone particles. Okay, so let me give it a rotation. Can you see where are those white colored foam particles which were distributed along the length? You can see they are all near the center. They are all near the center. In fact, there is an air bubble at the center, and all these foam particles are close to that air bubble. And are you able to see the red stone particles? Where are those red stone particles? Search where are the red stone particles. They were distributed along the length, and now you can see all of them are accumulated either at this end or at this end. The stone particles have gone outward. The foam particles had come inwards, and the air bubble, there is an air bubble out here, that also came in the middle. Stone particles are going away. That can be understandable from centrifugal force. The centrifugal force is outward, and that takes the stone particles away. but how come the air particles are coming towards the center, and how come these foam particles are coming towards the center? Once again, you have pressure difference in water. In rotating frame also, you have a pressure difference. The pressure of water near the edges is more and the pressure near the center is less, and that force of pressure difference is inward, whereas the pseudo force is outward, and whether it goes out or it comes towards the center is decided by who dominates over which one. Whether the pseudo force is more or the pressure difference is more, that will decide which particles will come towards the center and which particles will go away from the center. So let's take some experiments on rolling. You know, when a wheel or a sphere or something rolls on a surface, then different particles of this object move with different velocities. The point of contact, velocity of the point of contact is 0. That is what is when it is pure rolling. So this surface is fixed, this surface is fixed, and if this V is not 0, velocity of the contact point is not 0, then it will slip, and pure rolling means there is no slipping, and therefore this V contact should be 0. Whereas the center is of course moving with some velocity, say Vc, and if you look at the topmost point, it is moving with some more velocity, let us say V top. If you look some point somewhere here, that is moving with some other velocity, that will be moving with some other velocity. So different points move with different velocities, and a simple rule is this: take this as the instantaneous axis of rotation through the point of contact, and then you can use V equal to R omega to find the velocity. So if you look at this point, top point, this distance is 2 times radius. If you look at the center, this distance is radius. So V top is omega into 2r, and V center is omega into r. That means V top is equal to 2 times Vc. The velocity of the topmost point is double the velocity of the center, and my experiment will just demonstrate this fact. So I have this cylindrical object. This is just a PVC pipe, very commonly used in many purposes, and I am putting it on this horizontal surface, and it can roll here. It can roll here. So I put it at the edge, and here is a plastic scale, and I am putting edge of the scale right here. And my experiment consists of pushing the scale gently in the forward direction, so that, and pressing this PVC pipe, so that there is no slipping between this scale and this PVC pipe. It doesn't slip like this. Okay, so I'll just press it gently and slowly push it forward. You can see that the PVC pipe is rotating, rolling, it's going ahead, and at no point of time I am allowing this kind of slipping. So that means the speed of the topmost point of this PVC pipe is same as the speed of the portion of the scale which is in contact. So if it is here and then I am pushing it at this time, if there is no slipping here, the speed of this portion of the scale and the speed of this portion of the PVC pipe, the topmost point, they must be the same. So this is to be understood very well. Okay, so now let me start it. You see where is the edge of the scale and where is the center of the PVC pipe. Both are at the edge of this table. So this is the starting point, and now I am moving it. I am pressing it, at the same time I am moving it. and I am not allowing the topmost point to slip on this scale. So I have reached here. How much has the center of this PVC pipe moved? It has gone from this edge to this point. And how much is the scale has moved? This edge, look at this edge. This edge was here. This edge was here. And from here, this edge has reached here. So the scale has moved from the edge to this point, whereas the center has moved from the edge to this point. And if I measure this distance here, it is again one scale, 30 centimeters. So the center of the PVC pipe has moved 30 centimeters up to here, and this length is 30 centimeters. So this has moved 30 centimeters, but then the scale has moved this 30 centimeter plus this 30 centimeters, 60 centimeters. So you can see that in the same time, the center has moved 30 centimeters. The topmost point must have double velocity, because there is a scale which moves all the time with the topmost point velocity, has moved 60 centimeters, and so V top is double of V center. You must have derived the expression of acceleration when a sphere or a cylinder or a disc, they roll on an inclined plane. So if you have this inclined plane, some inclination theta, and suppose you have a sphere out here. Then if the friction coefficient is sufficient, it can come down with pure rolling. So it can rotate, it can move, and all the time you can have V is equal to omega times R, and acceleration of center as alpha times R. This is angular acceleration, this is angular velocity, this is linear acceleration of the center. So these conditions are satisfied, then you say it is pure rolling. So you can work out or you must have worked it out that what will be the acceleration of this. So it depends on the moment of inertia. If it is a sphere, you can work out what is the acceleration. If it is a cylinder or a disc, you can work out what is the acceleration. If it is a loop ring, you can work out what is the acceleration. And for doing that, you have to write the force equation, you have to write the friction, and remember, friction is not mu times n, because it is a static friction which is here. So whatever is necessary, only that much friction will be there. And then you write the equations, all do this components, and write the equation for the center of mass, and then the equation for angular acceleration, and then impose these conditions, and you can find all these things, and they are different. And you must be remembering that this acceleration of the sphere will be more than the acceleration of the disk, or vice versa. You revise that. I'll show it here. So I have made a prototype of approximate inclined plane. This is nothing but the channel, PVC channel used by plumbers and electricians, and I have made one side lifted so that it is approximately an inclined plane. Of course, because of its own weight, the shape is not really plane and all that. Then I have two objects. One is this cylindrical object or a disc type object. This also, you know, it's a carom coin. And the other is this kancha, this glass ball, that also is you are familiar with. So the idea is to compare the time these two take when they are rolling on this inclined plane. So I have this ball here, this spherical ball here, this is that kancha, and the disc is put here. And then I am putting this scale here, so that when I lift the scale, these two things will roll along this inclined plane. Okay. So now I am lifting the scale, and you see if the two are coming together, or one is faster, one is slower. So which one came earlier? The spherical one came earlier. Now let me reverse the order. I put this coin ahead and this spherical ball behind. They are coming together. So when I am putting this ball ahead, the spherical ball ahead, and this disc behind, then you see that the ball comes earlier and this disc takes more time. So the ball has a larger acceleration. But when the ball is behind and the disc is ahead, they are coming together. Not very unnatural, because the ball does have larger acceleration and disc has smaller acceleration. So the ball is pushing the disc, but the disc is there. It's not allowing the ball to go freely with its natural acceleration of whatever 5/7 g sin theta or so, and therefore they are coming together. So our next demonstration experiment is on angular momentum, torque, and especially the vector character of these things. So as you know, the torque is given by r cross f. The angular momentum is given by r cross p. Of course, these are for one force and one particle having this linear momentum. In a rigid body, you have many particles, so total angular momentum, you have to add these quantities. And for total torque, you have to find torque of every force and then add. And the important relation is that this dl dt is nothing but this torque. The change in angular momentum, the direction of that is same as the direction of torque, and the rate of change of angular momentum is the magnitude of this torque. So this is the important thing, and in our experiment we will try to see this, especially the direction part. Now the setup. Here I have a disc, CD disc, old CD disc used, and this has been mounted on the spindle of a motor. This is tape recorder motor, and we have mounted it here. Then with this motor we have taped battery, a cell, 9-volt cell, and the one end of the motor is already connected to this battery, and other end, if I touch it here, this motor will start rotating and the disc will also start rotating. So you watch the direction in which it starts moving, whether it is going this way clockwise as seen by you, or it is going anti-clockwise as seen by you. So let me just connect the motor and you see first the direction of rotation. So in which direction it is going when I am connecting it? Okay, so it is going anti-clockwise as seen by you, remember. And if it is going anti-clockwise, the angular momentum will be towards you. If it is going clockwise, the angular momentum is away from you. If it is going anti-clockwise, the angular momentum is towards you. And then this whole thing is hanged using this thread to this stand here, clamp stand here. So this other end of the thread is tied here so that it can just hang. And this point where we have put this thread, tied this thread, this point is specially chosen. If the disc surface is vertical, if this disc surface is vertical, this point is away from the center of mass of this system. And the center of mass will be somewhere here. The motor is the heaviest part, so it should be somewhere in the motor, and this thread is tied from this point, which is away from that, on the other side of the disk. So this is this. Okay, so this is the setup. First, let me analyze the situation. What happens if I leave this disk? I'm holding this disk here using my fingers and thumb. If I release it from here, what happens, and how do I analyze that? If you just release it, see what happens. The disk was like this, and you released, and the disk went like so. It's rotating. It's rotating like this. The disk is now in this vertical plane, and if I leave it, it rotates like this. So as seen from this side, it is going anti-clockwise. Okay. So angular momentum is 0 here, and then it is rotating anti-clockwise as seen from this side. So angular momentum is generated. So what is the direction of angular momentum change? It is in this direction. Verify if it is coming from r cross f. The force, the weight here, let's take the torque about the center of mass. So the weight here will not have any torque because it is passing through the center of mass, and this thread is there. So you have r vector from the origin to the point where this force is acting. So this is that r vector, and this is that force f vector. So if you have r vector something like this, if you have r vector something like this, what is this r vector? From the center of mass to the point where this thread is tied. So that is r vector, point of application of the force. This tension is the force, and here is the point of application. From the center of mass you join this, this is r, and this is f. So what is r cross f? R cross f is indeed coming in this direction, and therefore the direction of the torque and the direction of the change in angular momentum is the same as required by the equation. What happens when I connect this battery? If I connect this battery and it starts moving, and remember its movement is again anti-clockwise as seen from here. So you have large angular momentum in this direction. You have large angular momentum coming out in this direction. And if I release it, if I remove my fingers, what will happen? It will go with the torque here. Let me first analyze and then show. Okay. So if you have a large angular momentum already existing in this direction, and then if this torque is there, if I remove all my fingers, then it will only be because of this torque. And this torque we have already worked out. This torque direction is like this. This is r vector and f vector, and the torque is in this direction. Okay. So the change in angular momentum should be in that same direction. So suppose your angular momentum is already here, the disk is rotating fast, and then the change in angular momentum is like this. A small change in time dt is like this, because this is the direction of the torque. Work out r cross f. So that is the direction. So what will be the new angular momentum at time t plus delta t? At time t, this is the angular momentum, then this is the change dl in the direction of the torque, and if you take the resultant of these two, it will be like your parallelogram law, it will be something like this. So the new angular momentum must be in this direction. But new angular momentum in this direction means, and spinning fast, so the disk should be rotated. If the angular momentum is rotated and the angular momentum is perpendicular to this plane, so the whole disk has to be rotated, so it will go like this. So what I expect from the theory is that if it is not rotating, it falls. If it is rotating, it is spinning, then it will not fall, it will just rotate. So let us see if it happens like that. So now I am removing my fingers, and you see what happens to the plane of the disk, whether it goes down or it remains roughly vertical. You see the plane of this CD surface. It remains vertical, almost vertical. It's not falling. The CD is not falling. The plane still remains vertical and it is making this rotation. So that demonstrates that yes, the torque produces change in angular momentum, and the change in angular momentum is in the direction of the torque. So this is the essential reason why when you ride on a bicycle, when the bicycle is that wheel is spinning, is rotating, you can balance it easily. But if this bike is not moving, if this wheel is not rotating, and you don't have stand in your bicycle, you just cannot make it stationary there, it will fall. Now the last demonstration of this session is on forced oscillation and resonance. If you remember, an oscillating system has its own natural frequency. It can have more than one natural frequencies. So if you apply an external periodic force and then oscillations are under that, then it is called forced oscillation. And if the frequency of this external periodic force is close to the natural frequency, the amplitude increases. Okay? So you have an oscillating system, and this has got its own natural frequency, which you call omega naught, and this natural frequency comes through the restoring force mechanism that allows this system to oscillate. So that decides this. You can have more than one natural frequencies also, but sometimes you have only one natural frequency. And then you apply an external force. That means apart from that restoring force, apart from any damping force which may be there, you apply an external force, and if that is periodic, if this is also periodic and its frequency is omega, then if omega is close to omega naught, you have large amplitudes that is called resonance. And this omega and omega naught, if they differ from each other significantly, then the amplitudes are smaller. And I have an apparatus here. So I have a wooden block in which there is a groove here, and in that groove I have fixed a long straw. We have made this long straw by combining several straws, and then this end is just pushed into the groove. So this is the oscillating system. You look at the tip here, and if I oscillate, it just moves. Of course, there is a lot of damping, but before that, before it stops, it oscillates with certain frequency. This is the natural frequency. And I can apply an external periodic force on that using my hands. So look at my hands now at the bottom. I'll be just applying a, look at the fingers, I'll give this motion, periodic motion, so that this block also exerts a periodic force here on the straw. So I can just do this kind of motion. Okay? So let me first start with very low frequency of my hand. So look at my hand first. So I will be doing motion like this. Can you see I'm moving my fingers? Or you can look at this edge of the block. I'm moving this block with a very small frequency. And I will continue with this frequency, and you look at the edge of this straw, how that edge is oscillating. Look at the edge at the top. How is that oscillating? What is the amplitude? This is when the external applied frequency is small, much smaller than the natural frequency. Now I will be increasing the external frequency to a large value. Look at my hand. I am oscillating this stand, this base, with a very large frequency, and now look at the edge. Look at the edge. What is the amplitude? Not much. And next I will oscillate my hand. I apply that periodic force with a frequency which is close to the natural frequency. So first look at my hand. Look at my hand. Look at this wooden base. What kind of oscillations I am giving it to the base. Okay? And at this frequency, look at the edge of this straw. Look at the amplitude. How large is the amplitude? So at this time, the external periodic force has a frequency which is closer to the frequency, natural frequency of the straw, and the amplitudes are quite high. But if I increase the frequency, then you can see that the amplitude has gone really down, much less. And if I make my frequency of external force very small like this, then also the amplitude of oscillation is very small. But if I do this intermediate frequency very close to the natural frequency, the amplitudes are very high, and that is known as resonance. Okay, so with that I conclude this session. I hope you have enjoyed this natural phenomena which is there around us, which we can assemble in a very simple way, and which illustrates many of the physics principles that you learn in your theory classes. Thank you.